Hi, it's Ilya, and this is the second video in my VLA series. In the previous one, I talked about vision language action models and gave you a brief intro. And today, I'm going to talk about one of the most notable models in area of VLAs, Pi0 from physical intelligence. This video will have theoretical and practical parts. In the theoretical one, I will talk about the model itself and the overall architecture and some ideas used in this model. And in the practical one, I will discuss how you can fine-tune this model on your tasks, on your data sets, and for your robot. I will use my LeKiwi and the data set that I discussed in the previous video. While I was recording this video, the next iteration, the next version of this model called Pi0.5 was released. The model is very similar, and most of the things I'm talking about today are applicable to Pi0.5. But I will not focus on Pi0.5 right now, and I will release another follow-up video where I will talk more about the differences between Pi0.5 and Pi0. Pi0 is developed by Physical Intelligence. And I think that they're doing some of the most interesting things in robotics right now. So if you're not following them, please fix it. On average, once every month or couple of months, they post some interesting article or like new development, or they open source some code and so on. And today we will be looking at the Pi0 specifically. And as you can see, it's their like first generalist policy they developed, and they have this web page that covers a lot of things about it. So I highly recommend to just look at it, see how they demonstrate the policy in the real life, and also this page just provides some very brief summary of the policy itself and how it works, how it was trained, and what the results of this policy are. You can also go to the actual paper and read stuff in more details. I recommend to do it after you read everything on this page. And then they also have repository with open sourced code for training and fine-tuning of this policy. So we'll also talk about it a bit later. Okay, now let's talk about policy itself. Again, on the high level, it's a VLA policy, and I already talked about it and what it means. It means that this is the policy that is based on some LLM that also has a vision backbone, so it can look at different pictures, in our case on the videos from cameras, and it can predict the actions for the robot to complete very different tasks. And you can see that it was trained on the very big data set. So first of all, the fact that it's VLA means that they use already pre-trained VLM backbone that is trained on internet scale data. Also, they train the model on the OpenX robotics datasets collected with different robots. And finally, they collected their own dataset with different robots to fine-tune this model and demonstrate the performance in real life. They also train it and fine-tune it on many different problems. And again, just go through this site and you'll see that it can do like perform very different tasks. Let's talk a little bit more about the architecture of this model. In my previous video, I shown this general architecture schema for VLAs. And actually, Pi0 fits perfectly into the schema. So let's just update a little bit some of the components to make it more specific for Pi0. First of all, Pi0 uses SIG-LIP as an visual backbone. So this is the model developed by Google, and it's also trained in the VLM setup. This is why it works very well in VLAs. For LLM, it uses Gemma, and it is an open source LLM from Google. Consider it as a like little sister of Gemini. It's a small model that works pretty well. So there is already version 3 of this model. So maybe at some point the overall VLA or Pi0, like Pi whatever number is, we'll use beta Gemma version. If we combine Gemma and SIG-LIP, there is a name for it. It's called PolyGemma. Again, this is just VLM from Google that, simply speaking, just Gemma with SIGLib connected together and trained as a VLM. And this is exactly what Pi0 uses as a baseline pre-trained model before training on the robotics dataset. And then, so the state in this model is treated just a little bit separately inside the same transformer. But there are two ways actually to predict actions using Pi0. Way number one is to use fast tokens. I will not go into details, but fast is the way of actions tokenization developed by physical intelligence that uses some principles that are used for image compression and so on. You can read about it on the website, and yeah, it's like very interesting approach to do tokenization. But the idea is that yeah, so in this case, if you use fast, then we predict the action tokens directly from the VLM. And this is one of the options how to do it. When we look at the fine-tuning part, on the more practical part of this video, one of the options will be to train this fast model instead of the whole version of Pi0. But the more default way to predict actions is to use flow matching action expert. So this action expert uses flow matching, as you may guess, to denoise actions and generate the sequence of actions that we want to predict. And this denoising process is conditioned by outputs and internal outputs of VLM. So if we combine all these things together, we will get Pi0. So again, this Pi0 perfectly fits into this logic that I described. By the way, Pi0.5 fits even better, because in Pi0.5, both like fast tokens and flow matching based actions predicted simultaneously. So it also will be kind of the same on the schema. But again, I will not go into details of it right now. But what is interesting and what is actually unique for Pi0, or at least not so widespread, is how this flow matching action expert is connected to the LLM or like VLM part. Because it's not simply using cross attention to look at the output of VLM. It's connected on like every layer, and actually this flow matching is not fully separated from LLM. It's kind of continuation of the same LLM model that connected layer by layer. It just has a separate set of weights for queries, keys, and values inside attention. So it's like very, I think, interesting. For some reason, physical intelligence don't pay much attention to it when they talk about Pi0, but I think it's like very unusual way to do it. I want to go deeper into details and discuss how it works. To understand what is so special about the way how Action Expert and the VLM are connected, we need to first discuss how attention works. It's not the main topic of this video, so I will not go into all the details. And I assume that you have a high-level understanding of transformer architecture and attention logic. But just to make sure that we speak the same language, I want to give a quick intro in self-attention and cross-attention, and then discuss how actually Pi0 uses these mechanics to generate actions. First of all, let's look at the self-attention and how it works. Self-attention takes some tokens as an input, and usually these tokens representing some data from the same domain. It may be, I don't know, some text tokens. It can be tokens representing some patches of the images, embeddings of some events that are happening sequentially, and so on and so forth. Let's say we want to look at one particular vector. In this case, it's like the fifth vector out of 5 inputs, and we want to see how computations for this vector work. So first of all, we compute the query based on this input vector, and then we compute keys for every input vector that this vector can attend to. For simplicity, let's assume that it can attend to all 5 vectors here. And then by comparing this query and keys, we compute attention weights. So basically, we compute some weight for each input token, such as the sum of these weights equals 1. Then we apply another matrix on top of the input vectors and compute some values for each of these vectors. And then we average all these values using the weights that we just computed and generate some weighted vector v. And then we combine this vector with the original vector for which we make the prediction, put it through the feed-forward network, and get the output. Of course, I simplified a lot of things. There are also like a couple of skip connections here. But the idea is like this. So we take a bunch of vectors from the same kind of domain, from the same modality, same distribution usually. And then we do some manipulations with them. We compute the weights with which we want to attend to each of this vector, and then compute the like weighted value and use it in feed-forward layer. So this is what's happening in the self-attention layer that usually exists in any transformer. The second type of attention called cross-attention. And it's very, very similar. So most of the math behind is exactly the same. The main difference is that you have like two types of input tokens. So you have the actual input tokens, and also you have memory tokens. And these two types of tokens can be from completely different domains. So they can be completely different. So this memory can be already some processed data that we use for like conditioning, and this input tokens is something we use to make predictions for. And the overall logic is exactly the same, but when we compute all these keys, values, when we compute the weights, we don't take into account any other input tokens, or don't even take into account the actual token except computing the query for it. But instead, we do it for the input memory vectors. So what it means that we can freely deal with data with two very different domains. For example, this memory and input tokens can be like completely different, but when we compute queries and keys, they become a bit more comparable, and this is why we can compute all the rest of these things. And then we do absolutely same things. We weight all the vectors values using these computed weights and combine it with original vector and put it through feed-forward layer. Again, it's very, very similar in terms of math. The only difference is that for keys and values, we are not using input tokens. We're using some memory tokens that can be completely different, that can come from very different distributions, very different type of data, and so on. And the most default and the most classic way to use these two types of attention is following, like in the original transformer paper. So we somehow encode some inputs that we expect to use for conditioning, expect to use as memory. So let's say we can encode them using transformer, or in this case, actually doesn't matter. Maybe we just generate memory somehow else. Let's assume that we do it using transformer encoder here. And we, as an output of this model, we generate some kind of conditioning memory vectors. And then we have another part of the model, let's call it decoder here, that uses both self-attention and the cross-attention layers. So self-attention layers look at all the inputs of this decoder. Cross-attention layers look at the memory that we already computed using encoder. And this approach, like with two steps, allows to look both at the input data, that again, presumably some very similar data from the same domain, and every like second step also look at the memory that can incorporate a lot of conditioning information that can be based on very, very different domain, very, very different type of data. And then by iteratively applying these things, we get the output of decoder. So in case of VLA, our encoder can be our like original VLM, and our decoder will be some kind of action head, or action expert, as it's called in Pi0. Also, sometimes you have a lot of useful information somewhere in between, so somewhere in, not after the last layer of encoder, but somewhere in the middle, because usually the last layer is overfitted to, let's say, predict next token or solve some particular task that was used for pre-training. But some middle layers can have very useful, important, and high-level information that can be much more useful for our particular task than the latest layer. So sometimes it also makes sense to actually connect this cross attention to some internal layers output of the encoder. But now let's look at how it works in Pi0. In Pi0, it looks actually very different. So the blue part corresponds to BLM of the model, and this pink part corresponds to the action expert. And you can see that there is no cross attention at all. So Pi0 transformer uses only self-attention layers. There are more than 3 of them. Of course, I just shown 3 for simplicity here, but it uses only self-attention. But the way how it's done is similar to the mixture of expert approach, even so it's slightly different. And the idea is that you actually have different weights for computing keys, values, and queues for the VLM part and for the action expert. But when you actually compute the attention, you use all of them together. So you don't really have 2 separate parts of encoder and decoder. You have like one big transformer with 2 sets of weights. I'm not sure if there is an official name for it. I called it fused attention layer. And the idea is that you still have 2 sets of tokens. One is coming from VLM, so it can be your images and text input. And another set of token is noisy actions that you try to denoise using flow matching approach. And the idea is that whenever you compute some weights and values for, let's say, this last vector representing the false noisy action, then you look at everything combined. You compute keys for VLM tokens using some set of weights. You compute keys for your action tokens using another set of weights. But then you compute the actual weights, actual attention weights for all of these vectors together. You kind of concatenate them and compute the weights together. And the same for the values. You compute them using separate matrices for VLM and for noisy actions, but then you combine them together using these predicted weights. And then you use like only one vector from both VLM tokens and noisy action tokens, and do the same stuff as you do in all other types of attention layers. So again, you can see that it's slightly different, or maybe significantly different, from cross attention and from self attention. And to be honest, I'm not sure what the benefits of this approach are. I read the paper and read like some extra comments from the physical intelligence team, and even so, this change is very unusual and big in terms of impact on architecture, I guess. They don't really talk about it much, and they don't explain why do they believe that this approach is better than completely separated action expert. I can think about one benefit is that they save some weights, and it computes faster because you don't need to do self-attention and cross attention separately. But yeah, this optimization is probably not so big. And but at the same time, I don't think why it's supposed to perform better than separate expert transformer, because this data, VLM tokens and noisy action tokens, are from very different domains. So there is no reason to kind of try to squeeze noisy actions in the same domain as VLM tokens on every single layer of these transformers. So I cannot explain what's exactly the idea behind it, and the team behind this model don't explain it either. So yeah, I'm not sure what is the actual rationale, and I also didn't see any ablation studies around it. So yeah, like my gut feeling tells me that if this part, the action expert, would be like separated, and we'll just use very classic cross attention and self attention approach, it will work better. But again, it's just my guess. I don't have like any proofs, and I don't have enough data or experiments to test it. But if you've seen any papers where people try to separate it, specifically for Pi0, please let me know, because I think it's an interesting topic I would like to learn about it. In the original paper, they refer to the mixture of experts logic. And yes, implementationally, it's very close. It's kind of done in the same way. But in case of mixture of experts, there are like different experts that deal with the same domain of data. So there is no different data domains. There is no different data modalities. So I don't think that there's like exact comparison. And anyway, in Pi0, only one action expert is used. There are no like 10 experts that are applied depending on whatever is predicted. So again, it doesn't use the main benefits of mixture of experts. So yeah, I don't know what's the actual benefits of this approach, but it's pretty interesting. It's unusual, and maybe there are some hidden reasons why it actually works. And I would actually like to learn about it if someone knows about it. Another interesting thing is that this model, this policy, doesn't have any robot-specific action head or adapter. So it means that there is only one output of this model, and it outputs actions for all the different robots at the same time, kind of. Imagine during the training, in one batch, you have some samples from, let's say, 7 different robots right here, and then you make prediction, some vector of actions, and for each robot, the meaning of these actions in the same vector will be different. So for example, when you're looking, let's say, at 7th action, for some robot, it may mean the position of the gripper. For another robot, it can mean the, let's say, position of the wrist. And it's very interesting. They don't adjust the code, or they don't adjust the model for any specific robot, but somehow it works, and somehow the model managed to learn how to control simultaneously all these robots. I don't think there's like official explanation of how it works. They don't talk too much about it, but I can like speculate a little bit. So I think that for inference, first of all, this model is not supposed to work out of the box. Yes, so you expected to fine-tune your model, and when you fine-tune your model, then you have like a data set for this specific robot where you use it, and during this fine-tuning, it learns to predict actions for your specific robot. So this one is easy. During the training, like an example that I just gave you, when you have multiple robots in the same batch, I think the best analogy I can think about is computer games. So let's say you have a joystick, you have a like gamepad, and you can play different games using this gamepad. It has a limited number of buttons, of keys, and the thing is that you learn how to use them all the time, but they have different meanings in different games. So in one game, like this button can mean jump, in another it means go forward, and so on. And you simply look at the screen and you remember what game you are playing right now, and you understand what the meaning of each button. So it's kind of similar, I guess, for the policy when it learns how to control different robots, because it has the fixed output. Let's say each dimension of the action vector is one button, and it learns how to press these buttons, and then it simply looks at the robot, it looks at the input data, it looks at the pictures that it receives, and it understands that in this particular case, these buttons mean this one. In this particular case, these buttons mean that one. This is why it allows it to predict like different actions using the same action expert. Again, it's very interesting. I didn't see in the paper whether they provide any experiments where they try to train like separate heads for separate robots, and whether the approach really better than this one. But anyway, like it works and it's cool. And but yeah, it would be very interesting to see if someone experiments with slight modifications, so like separate heads, or at least separate, I don't know, linear adapters in the very end for different robots, and say whether it improves the results or not. Now let's talk about the practical usage of this model. As I talked before, current existing VLAs are not supposed to be used zero shot, so it means that you need to fine-tune this model. It means you take the model that is pre-trained on the massive amount of data, and then you collect some relatively small data set using your particular robot, and where your robot completes your particular task that you need. And then you do a little bit of extra training of this policy on your data set. I talked about the data set that I'm using here in my previous video. So I collected it using LeKiwi robot, and it's very simple pick and place problem that I'm trying to solve there. And yeah, this data set contains around 15 minutes of data, and there are 55 episodes in total. I will show how to fine-tune Pi0 model using OpenPI repository. I will talk about the overall fine-tuning process, different options on how you can fine-tune the model, and of course, I will show the results and discuss some findings and my observations. My dataset is published on HuggingFace. I will provide the link to it in the description. As I mentioned before, Physical Intelligence also have this repository where they open sourced their models, Pi0, Fast, Pi0.5, and so on. And actually, it's pretty nice, and it has nice instructions. And I would say if you just follow these instructions, you will be able to fine-tune every model. I didn't face any big problems at all. There are a couple of ways to fine-tune Pi0. The first one is to use this official repository. And in this repository, the main model is written on JAX. And even so, I'm not very proficient with JAX and prefer PyTorch. I tried to use this model, and there were no problems at all. So you don't really need to understand JAX to fine-tune the model. And even if you want to look into the code, it's pretty straightforward. Without understanding of JAX syntax, you still can understand everything that is happening there. That is very nice. It's very high quality code. I liked it. And another thing that you can see right here is that they just released PyTorch support in the official OpenPI repository. I think it's still a bit limited, so you don't have all the flexibility with PyTorch that you have with JAX. So I prefer the original version. And another third version that you can use is just use the LeRobot library, and they have their own like half official re-implementation of Pi0 policy. But yeah, again, this is up to you. You can try any of it. I prefer to use the most original one. To train this model, you usually need quite a lot of compute. It's recommended to train your model on some graphic card with more than 70 gigabyte of memory. And I don't think people usually have this type of cards at home. So just use cloud for this. I personally just rented some GPUs in cloud to do this training. Training of the model will probably take few hours depending on your dataset size. And currently, top GPUs cost around $2 maybe to rent per hour. So let's say if you are training a model for like 5 hours, it will cost you around 10 USD in total. So yeah, it's up to you, but it's definitely cheaper than buying a very professional GPU. So yeah, I highly recommend you to use this cloud compute. And also I provide a script that allows you to set up the cloud much easily than usual. I published this script in my GitHub, and I use remote machines quite often to do some model training and so on. And it usually takes some time to set up, to install all the libraries. So I created this script that actually installs a lot of redundant libraries. I think most of them are actually not needed in most of the cases, but I basically added any dependency that caused any troubles or solved any problems for me in the past while I was setting up the machine for the LeRobot. So yeah, there can be like some things that you probably don't need, but I think it's usually fine because you usually run this machine, you spend a few minutes setting it up, then you train the model, and then you completely remove everything. So you don't really care if you like install some extra packages, and this is what I'm doing. So yeah, this script allows you to install some Linux packages, then install all the like conda packages that are needed, install UV that you also need to install OpenPI, and also it logins you to weights and biases and HuggingFace. So again, nothing extra happening here, just very simple installations, just inside one script. I usually use it because it's much more convenient than doing it manually every time I need a new machine. So I released it in my GitHub, so yeah, you can also use it if you want. After you set up your machine, you need to install OpenPI. And again, it's very straightforward. Just git clone and then install UV. And again, UV is installed in my setup automatically. And then install this repository, and everything's supposed to work. It's very easy. I don't think you will have any problems here. Just very straightforward package installation. Just follow the original instructions. You may see that there are different models that you can fine-tune. The first one is Pi0. We will mostly talk about this model today. The second one is Pi0 Fast. I will also talk a little bit about fine-tuning this model, and I will provide some code that helps you to fine-tune it, but I will not spend too much time on it. And finally, there is Pi0.5 that was just added a couple of days ago, and I will not talk about it now, but I will talk about it in the next video. You can also use some fine-tuned model if you have one of these robots mentioned here. I don't have it. I fine-tune it on my own custom LeKiwi, so I need to fine-tune it from scratch using base model. Conveniently, you can use LeRobot dataset to train this model. So you don't really need to convert anything in the dataset, just use it as is, as we collected it, as I shown in one of my previous videos. So if you collected it using the recent LeRobot, you don't need any conversion, and you can skip the first step. The second step is probably the most complicated. This is when you need to write some code. And again, it's pretty easy, and repository provides a lot of examples. So you just need to follow these examples, and it will be very easy to do. So the first thing that you need to do is to create this config file for your robot, if it doesn't exist yet, and update everything to make sure that it's aligned with your dataset. OpenPI repository contains multiple files like this for different robots, and they have a lot of very detailed comments that explain what's happening here and what exactly you should do. So if you have any questions, just open a couple of different files and try to see how it works in different cases, and you will understand what you're supposed to do for your particular robot and for your particular dataset. I published the config file that I use for training in the same repository. And basically, the main thing that this file contains is just code that aligns the names of inputs in your dataset and what the model expects. So I think most of it is very straightforward. You can just follow the examples that are provided in the library itself, or you can look at my file as another example. I think the most tricky part for me was this one, where you need to align the names of the cameras. And the problem is that Pi0 expects 3 cameras, 2 from wrists, from left and right, and one from top, and or like base, maybe not exactly top. And the problem that I don't have 2 wrists in the robot, so I have like top camera, front camera, and wrist camera. And I just decided to use front camera instead of right wrist camera. And then I use top camera as base and wrist camera as left. I wasn't sure if it would work or not, but it worked. So probably if you have another 3 cameras, it's still fine to just replace one of the wrists with unexpected camera. So again, in my case, it worked well, but yeah, this one was the only tricky part. Again, the rest is very simple. If you don't understand something, you can just try to read through more examples. There are a lot of them, and all of them are very heavily commented. The second file that you need to adjust is training config file. So this file, you don't need to copy it. You need to make some changes inside the file. So if you scroll through it, you'll see that this file has many different data classes that define different types of data sets that can be used for training. Again, there are a lot of comments. There are a lot of examples. There are like different examples for different types of data sets, for like different robots, for different policies, and so on. So if you are like confused and don't understand what exactly is expected somewhere, just try to go through few different examples, and you will probably find the answers for your questions. So you need to create one more class defining the config for your data set. And you also need to add at least one train config in the very end of this file. And this train config will reuse this class that you define and also set some other parameters for the training. And again, I provide the example of the config file that I used. And I don't provide the whole file. I provide only the things that you need to add, or like what I added to train in my case. So first of all, you need to import the file that you just created in the previous step. Then you need to define this class of data config. And again, most of the things are very, very well commented. Just follow the examples from different configs that are presented in that file. The main thing that you need to do is to align the naming of inputs and outputs in your data set, and what the model expects and what is used inside model. This is one thing. Another thing that is also important is to set up this delta action mask correctly. I will show you a bit later that I actually made a mistake originally here. And the idea here is that Pi0 uses delta actions, and my dataset recorded the actual actions. So I needed to convert actions into delta actions for the first 5 actions, for the first 5 motors that control the actual arm. But I don't need to convert the gripper, and I don't need to convert velocity actions because in my case they're always 0, so it's just better to keep them 0 instead of transforming them to delta actions. But again, it should be very straightforward. Just need to align with your robot. You need to transform all the joints, positions, actions into delta actions and keep the rest as is. So velocity and gripper positions are fine to keep as is without this transformation. Again, at least this is how it worked for me, and I think it was the original intention for this parameter. And yeah, and this is it. So you don't need to write all this stuff yourself. I think most of the things is already there. You just need to change just a few parameters. Just copy paste another config and just change a little bit. And then finally, you need to create training configs. So for every type of model that you want to train, you need to create one more config and add it to this configs list. And again, there are a lot of examples. You just follow these examples, and it's pretty straightforward. I created here 5 different configs. 2 configs for Pi0, one for LoRA training, another one for the full training. Then 2 configs for fast Pi0, again, one with LoRA, one without LoRA. And finally, I also added the config for Pi0.5. So actually, you can just use all this code that I provide today to train Pi0.5, and it will work. So it's already working code. And yeah, I think you don't need to change many parameters. Mostly just keep everything default. Again, maybe if you go deeper into optimization, you need to change more of them, but most of them are pretty straightforward. So I think one parameter that I actually changed and it helped is action horizon. So default one was a bit too long for my robot. I set it to 30. Then I updated the training steps. 5,000 steps seems to be like more than enough in my case. So I keep it short, and the training works very fast. And the rest, again, is pretty straightforward. You need to update like action deems for your robot. You can choose the action horizon that you want. So yeah, again, just simply follow instructions. There are a lot of examples. There are a lot of comments. Just follow them, and everything will work. So this code that I provide is just one extra example, but again, the original authors of the library created a lot of them with a lot of detailed comments, so it should be very easy. All these things that I've just been talking about are listed here. So after you did all these changes, you need to adjust 2 files. You can start fine-tuning, and you need to do 2 things. First of all, you need to compute statistics. Just run this script to compute your statistics. Just replace the configuration name with the name that you just created. And after the statistics are computed in a couple of minutes, you can finally start the training. So again, just run the script, replace the name of training config with your training config name, and that's it. It will train yourself automatically. It will sync with weights and biases, so you'll see the training progress there as well. The number of training steps that you need will probably depend on the size of your data set and on the complexity of your problem and so on. For my very simple problem, as I mentioned before, I just need a few thousand steps to train the model. It takes at most few hours, depending on the GPU that you use. And as I said, it will probably cost you up to $10 to actually fine-tune Pi0 on some small data set. Pi0 supports both full fine-tuning and LoRA fine-tuning. LoRA is the technique that allows you to fine-tune very big models using much less memory than straightforward full fine-tuning. And even so, it's not the main topic of this video. I will talk about results of both LoRA and full fine-tuning later when we discuss the actual performance of the models. Usually LoRA takes less resources for fine-tuning, but the results are a bit worse whenever you do it for any model. And yeah, in my case, I think that full fine-tuning actually works pretty fast anyway. So I would recommend everybody to go for full fine-tuning. But yeah, let's also discuss what LoRA is. And later in the video, let's discuss the results of LoRA fine-tuning of Pi0. Let's quickly talk about LoRA, about low rank adaptation. And to understand how LoRA works, we need to understand how any neural network works. So basically, neural network is just a bunch of matrices with different numbers and with some specified order of operations with them. So basically take an input that also some vectors or some matrix of different numbers, and then we multiply some other matrices, add some matrices, apply some other non-linearity on top of them, or do some other actions with them. But yes, eventually it's just a lot of operations with matrices, mostly multiplications, but a lot of other operations as well. And the problem is that we have a lot of them, and all these matrices have a lot of parameters. So all these VLAs have billions parameters right now. And let's look at some examples. So let's say that somewhere in the middle of our model, we have one matrix 1000 by 1000. So this matrix has 1 million parameters. And if we decide to train our model, or if we decide to fine-tune our model, we will need to update this 1 million parameters at every fine-tuning step. This is exactly how all these models are trained. We update these parameters little by little, every single step. But the problem is that it's computationally expensive to update such a big number of parameters. And also, usually all these big models, they have a lot of redundancy. So in practice, to fine-tune your model on some task, you probably don't really need to change all the parameters. It's enough to change just a few parameters that are somehow very well selected to improve the quality of the model on the particular tasks. And this is why LoRA works. So the idea of LoRA is very simple. So instead of optimizing these million parameters, let's freeze this original matrix with 1 million parameters and also create initially random two matrices. One matrix 1000 by 10, another one 10 by 1000. The main trick is if we multiply these two matrices, we will get another matrix that has the same number of parameters and the same shape as the original matrix, so we can add it on top of this original matrix. But this new matrix has only 20,000 independent parameters because it's completely defined by these two small matrices, and it's generated by just multiplying them one by another. And then if we do it like this, and we replace the original matrix with the sum of this matrix plus this multiplication of two other matrices in the model, and then we freeze original matrix and unfreeze these two matrices, then eventually, as a result, we will have the model that has completely identical architecture to the original model. All the matrices, they have the same shapes and so on. But the number of trainable parameters is significantly smaller. So instead of trying to adjust 1 million parameters, we need to adjust only 20,000 parameters. And we do completely the same thing for all or like most of the matrices in our model. And eventually we reduce the amount of the trainable parameters significantly. And it allows us to train our model much faster. And also, it's very crucial when you fine-tune on a very small data set, because when you apply this LoRa fine-tuning, you your model don't really forget the original weights. So it doesn't forget the original like pre-trained knowledge and so on and so forth. That can be the problem with fine-tuning on the small data sets. It just makes some very, very like small, relatively small adjustments for all the weights to optimize for your problem. When you use LoRa, your model is regularized, not around zero weights, but around the original pre-trained weights. And it has a lot of benefits, especially when you fine-tune on very, very small data sets. And this is how it's done. And the best part of it is that you can actually merge everything together in the very end. When you finished your fine-tuning, you simply update your original matrix with by adding this new matrix to it, and save it into the model that looks exactly the same in terms of the shapes of all the matrices, looks exactly the same as your original model. So after this fine-tuning, you don't have any extra computations during the actual predictions. So yeah, LoRa is like very convenient way to fine-tune big models. It's used very, very often currently, especially with LLMs and other very big models. And finally, after the model is trained, you can run inference on your real robot. And there is some code provided here, but I prefer to run my robot and control it using LeRobot. So I created some wrapper for LeRobot that allows you to run Pi0 policy, original policy written in JAX, and control the robot using LeRobot directly. I'm sharing this file in the same repository, and it's very simple and straightforward. So what it's doing is simply initializing the model and loading it from HuggingFace hub. Then it's connecting to the robot. In my case, it's LeKiwi, but again, you can easily update it to work with any other robot supported in LeRobot library. And then it's simply running a while loop. And in this loop, it makes predictions and then uses actions from these predictions to execute some amount of actions. And then when all the predicted actions or specified amount of actions was executed, it goes again to prediction, run the model, and generates a new chunk. And basically, that's it. Nothing else is happening there. Nothing else is happening in this script. And so a couple more things. So you can specify 3 parameters on top. The first one is FPS, in which you want to execute your actions and just set it to the original FPS of your robot. The second one is task description. So this is the prompt that you send to the model. I will show you later in the video that if you train it on the very small data set, it doesn't really work. It's just learn to complete only one task. If we deal with much bigger data set with multiple problems inside, that probably this task description is important parameter for you to use. And finally, actions to execute is kind of a trick that allows you to execute less actions than you predict in the chunk. So for example, if your chunk prediction is 50 actions, you can execute only 20, and these 20 actions will be much more precise than the latest actions in the chunk. So I've seen some significant boost in success rate when I added it. And again, I will talk about it very soon in the part about my experimentation. So you can use the script to run pre-trained model using the robot library. I do it all the time when I experiment with my robot. So that's it. As you can see, it's pretty easy. You just follow all the official instructions. And if you just do it, you will be able to fine-tune your policy and use it on real robot. And as I said, you can even run it using LeRobot with my simple wrapper. So we don't need many changes to do it. And you don't need to convert model to PyTorch and so on and so forth. It's already working well. So yeah, now let's discuss the actual results of fine-tuning, and let's look at how it works on the real robot. Yeah, if you come back to this page, you can see that physical intelligence provided a lot of cool demos, and the robots doing a lot of different things in real world, very useful. I'm not sure, but I think, based at least on like papers that I read and so on, I think that to really have these very cool results, to have all this generalization, you need much more data. So probably if you have like I don't know 100 hours data set, or if you use one of the robots that they use, then you can expect some generalization, some very complex tasks, and so on. In my case, I just want to show you how it works if you fine-tune it on a very simple robot on the very like simple task in a very small data set, simply because I don't have access to other robots, and I don't have I don't know 100 hours of free time to collect more detailed data set. So yeah, like again, if you're experimenting at home, don't expect such cool results like here. But yeah, let's just look at what I managed to achieve by fine-tuning this policy on my robot at home. Okay, and now let's look at the actual results that I managed to achieve. And just to give you a summary, everything is aligned with my expectations and with what I said in the previous video. I would say that Pi0 works very good as initial initialization, very good as pre-trained model, because just in a couple of hours, or like maybe 3 hours of fine-tuning, I can achieve pretty good results on my problem. Usually it took me longer to actually train the single task policies from scratch. So I think it's a pretty nice result. But at the same time, there is no generalization. So I don't absorb any like prompt following. The policy cannot really control my robot to do any other tasks after being fine-tuned on this simple problem. But again, this is completely expected. So if you want your policy to follow your language commands and generalize across different tasks, then probably you need much more data. So like if you have, let's say 100 hours of recordings with the same robot for different problems, with different prompts and so on and so forth, then probably you can get some generalization and achieve results similar to what you can see on the official Pi0 page. I deal with much smaller data sets with much simpler problems, so I don't really see all this cool generalization features. But again, it works very well as the initialization for the model when I train it on the single task. So yeah, let's look at the results, and let's go through the steps how I managed to achieve these results and what I observed during the training, during the iterations of my experiments. So first of all, I tried to train the model with default parameters. I've taken the LoRA version of the full model with Action Expert and simply train it without changing any parameters at all, and then try to run it in the real robot. You can see the results here, and you can see that the robot is doing some reasonable things. It's moving in the right direction, but it makes a lot of mistakes. The success rate is very low. But if you look closer at what's happening, you can see that it's usually doing right actions in the beginning of the action chunk, and then doing some not very precise things in the very end.
So by looking at it, I realized that default length of action chunk that I was using is too long for my task. The default length is 50, so it predicts next 50 actions every single time. Given that my setup has FPS of 30, it's probably a bit too much, so it's trying to predict actions into like 1 and 7 seconds into the future. So yeah, it's probably too much, and this is why I added this parameter that I've shown you in the evaluation script that allows you to execute less actions that were predicted in the action chunk. And let's see how it works when I make this simple fix. So what I'm doing here, I still using the same model as before, exactly the same one. The only difference is that at every prediction step, when I predict 50 actions, 50 next actions in the chunk, I execute only 20 of them. So you can see in this video that the movements became a bit like shorter. It moving much less at a time. But the idea is that the longer your action chunk, the higher errors will be for the latest actions, because these actions, they keep accumulating when you make these predictions. And it seems like it's much better to predict like shorter chunks, and it can be important parameter for you to optimize. So here again, I didn't change anything in prediction, even so it's possible to do. I just use the same model. It simply adjusts how many actions in the chunk I use for every prediction. And you can see that this model works much better, and it completes the task almost every time. And this was the first model that I would say actually worked. But if you look at the video, you can see another issue. So if you look at the wheels, you can see that they are moving. And this is strange because, yeah, first of all, I recorded the dataset as dataset for LeKiwi. So I recorded these wheel speeds as well, but I never used them. So literally the whole dataset that I have, wheels are never moving there. And I thought that for any model, it will be very easy to learn that the predictions, the actions for wheels should always be 0. But it seems like in this case, it's not true, and the robot is moving randomly a little bit all the time. And the reason for it was, I would say, incorrect configuration. So Pi0 transforms your actions into delta actions for training, and you need to actually specify which actions you want to transform to delta actions and which actions you don't want to transform. And again, by default, it transforms, and I kind of skipped it. So I think I transformed the velocity actions into delta actions, and it doesn't make too much sense. And then maybe because they're close to 0 and there was some noise in states, they kind of scaled it to some high values and started to predict this random noise. So yeah, in my latest config that I present in my repository, I fixed this issue and correctly treat the states, and robot is not making this random wheel movements anymore. You can see that this model works already pretty well, but actually I think that in this case LoRa training does leads to some drop in performance. So as the next step, I decided to train the whole model, and I think the whole model has the best performance. So let's move to it and discuss the whole model now. So now I'm showing the results of fine-tuning the whole model without LoRa using Action Expert, predicting 30 actions per chunk, but executing 20 actions per chunk each time. So I think this is the model where I achieved the best results. And here you can see the first checkpoint that I actually tried. This is checkpoint just after 1000 training steps. So in my case, it probably took around half an hour to train this checkpoint. And you can see that it already has pretty good results. It's still not ideal, it makes some mistakes and so on, but generally it's doing very reasonable things. And yeah, I think that one of the big observations is that the model converges very fast. So if you are doing some training, then make sure to whenever you have your first checkpoints, just run them on your robot and try to see how it works. It already should do some reasonable things. Yeah, so again, you see sometimes it's stuck, sometimes it makes mistakes, and I need to help it, but sometimes it's actually pretty good, and it can complete the task and can put this ball inside the cap. Here, I just want to show you a few different videos of different models. Each video is real speed, and each video is uncut, so it's like it's just multiple consecutive tries done by one model. So they more or less, this video reflects the actual performance of the robot when I run it in different experiments. Also, I'm running my inference on pretty old GPU. So I'm running it on 2080 Ti GPU that is like 3 generations behind even for consumer GPUs, and definitely much less performant than the modern, let's say, professional GPUs. So it's not the fastest possible inference. Currently, it takes 800 milliseconds to make one prediction for this model. And as I said, I then run 20 actions that I just predicted. So this running these 20 actions takes another 700 milliseconds. So in total, every like second and a half, the robot executes 20 actions. So this is how it works right now. Again, a simple upgrade of hardware of GPU can probably make it much faster. Training a little bit longer improves results. So here you can see how model performs after 5,000 steps of training, maybe around like 3 hours of training in total. So I don't see big improvements after that. So I think for my case, for my data set, training for 5,000 steps is more than enough. And yeah, and now you can see that it can currently complete the task many times in a row. So you'll see it still makes mistakes sometimes, but sometimes it recovers from its own mistakes and manage to grab the ball even after a couple of failed attempts. But sometimes it, of course, makes big mistakes and still fail. This is probably the best performance that I achieved. Again, this is the full model without any LoRA. This model predicts 30 actions per chunk, and then I execute 20 of these 30 actions every time, and it takes around 1.5 seconds for this full cycle prediction and 20 actions execution. I will show you like around 5 minutes of uninterrupted video of this robot completing the task. And yeah, so rest of the video, let's just watch a little bit speed up. As we discussed before, instead of using flow matching, you can train Pi0 model with fast tokenizer, and it will predict action tokens after regressively. Yeah, this is kind of one of the alternatives that you can use for model training. In summary, I would say that in my experience, it didn't give any visible benefits. So you can see right now how this fast model works. So first of all, it has slower inference. So for one prediction, it takes around 1.2 seconds. So it's like 50% slower than with flow matching. And this is for 15 actions only. So it predicts less actions and it does it 50% slower. So you can see that it's not moving so fast. Also, I found that performance is worse, so the actions are not so precise usually, and the success rate of fast model is lower. That again is kind of expected. But the main claim of the fast model in the paper is that it converges faster, so the training should be much faster, and I should see the same results as with flow matching, 5 times faster. Again, this is what was achieved in the paper. But for my case, it's not true. So I also checked the snapshot after 1,000 training steps and checkpoint after 5,000 training steps. Yeah, like after 1,000 already kind of was doing some things, but it was more or less on par with flow matching results after 1,000 steps. And I think it never really achieved the same quality, the same success rate as the whole model with flow matching. So yeah, even so, it's kind of interesting concept. I think that flow matching overall works better. And again, in my case, I didn't even see the benefits of faster training. So I think that full model with flow matching works better. Another observation about fast is that LoRA fine-tuning version of fast, I would say, didn't work at all. So it was like very, very hard to make it work. In like many cases, it has issues with decoding, some decoding errors and so on, and the quality was even lower. So if you are training fast version and for some reason want to use fast version, I would recommend you to use full fine-tuning instead of LoRA fine-tuning. Again, this is just based on my experiment with this one small dataset. Okay, now we are back to the best model, to the flow matching one that I shown before. And I already told you in advance that I didn't expect much of generalization from the model, but I still wanted to try it just to test. So here you can see what it's doing when I give the model wrong prompts. So basically, as you remember, we can give text comments to the robot. And what I'm tried here, I tried to use different comments. So the original comment was to pick the orange ball and put it into the green cup. And here, I think I just asked it to grab the orange ball, lift it, and do nothing. I think when you change prompt, it slightly reduces success rate. But the point is that the robot always trying to complete the same task. So regardless of what you write in the prompt, it will try to grab the ball and put it into the cup. That is not actually what you want ideally, but this is how it works. So again, here I even removed the cap, and the prompt is to grab the ball and lift it and do nothing. But even after robot lifted, it started to look for a cup. It became a bit nervous, I would say, and started to look for a cup everywhere because it cannot just stay still. It cannot really follow the commands. Let's give it back so it can complete the task and relax. And now I left the prompt empty, so there is actually no command at all. It's just empty string. and robot is doing the same. Robot just simply learn to grab the ball and put it to the cap, so there is no command following. And again, I kind of believe that when you use the not original prompt, you reduce the success rate. So I think it works slightly worse, but it's kind of negligible. I didn't really measure it much, so I think that mostly the prompt is just ignored inside the model. One type of generalization that exists is that the robot is capable of working with different colors of balls and cups. But in this case, I'm not even sure if this generalization is good or bad, because prompt is still to grab the orange ball and put it into the green cup. So yeah, I'm not sure if it's good that it's doing this stuff with other colors of the balls and cups. So now you can see the confusion that robot has when there are two cups, and it usually stays very, very undecisive. When I show like two different cups, it's like every action chunk that's predicted, it's kind of changing its mind. Sometimes go to the green one, sometimes goes to the yellow one. So if you add two balls, there will be even more confusion. It is completely out of distribution sample. So in the training data, I always had just one cup, one ball, and they were orange and green all the time. So yeah, this is kind of the generalization test. So eventually it managed to actually grab some ball and put it into some cup. So it's not so bad. But again, don't expect any language following if you are training your model on a very small data set on a very simple problem. Also, small and funny thing, especially when robots see some very unusual environment, like multiple targets or the like completed problem already, it's starting to hallucinate a little bit and tries to like grab some phantom ball or whatever. So yeah, like I've seen it a few times, and yeah, it usually happens when you show some out of distribution things to the robot. And finally, I tested robot in different environments. So I just moved it around my house and tried to run it in different places. So here it's standing on my desk. It has like different background color. It has different picture in front of the camera. So I can see that it still can complete the task, and it's doing it pretty well. So again, I think the best performance in my observations was when I was running tests exactly at the same spot where I was collecting data. But when I moved it to other parts of my house, it still worked pretty well. So I didn't see a very, very big, significant performance drop. So I think it's capable of kind of generalizing, at least on this level. You see that sometimes it still makes mistakes, but yeah, overall it can recover, and in most of the cases, it can complete the task. Thank you for watching. I hope you enjoyed it and learned something new. And I will provide all the links for like everything that I mentioned, all the repositories, papers, and other resources in the description of this video, so you can find everything there. Please like and subscribe if you enjoyed it and want to see more videos like this. And also, if you have like any comments, any questions, or maybe you fine-tune your VLAs and get nice and cool results with your robots, please share all of it in the comments.
I usually read all the comments and try to answer and try to also provide some more detailed answers in the future videos if I see that there are like similar requests about interesting topics that people want to learn about. And yeah, like in the next video, I will talk about Pi0.5. This is the next iteration of Pi0 model. And so far in my simple test, it shows very, very good performance. So I will talk a little bit about the differences between models and also show the results of Pi0.5 very soon in the next video. And yeah, thank you again, and see you in the next one. Bye.